Okay, guys, welcome back to inverter circuit designing. And in this video, I want to just brush up on what we have done so far before we can now move to the next stage. So, based on the question so many people have been asking concerning the different parts and the issues, so I'm going to re-explain the entire circuit on this video, beginning from the power source. Here is the power source, which is the battery, a 25 volts. Some people had issues with the voltage. They went and used 12 volt, but this is a 25 volt inverter design. That's in other words 24 volts inverter design. And from here it moves through a diode. The purpose of this diode is to isolate a protect reverse charge from going back to the battery or to the transistor, the driver, the main transistor driver, because when the driver is feeding directly from the battery. So if the main driver is turned on, especially when you have an high load, it's going to force electrons to almost all the electrons to concentrate on feeding the driver because it has the highest load demand in the circuit. So because of this diode has been imputed in this place to prevent reverse. So whenever there is that drag in the circuit, it won't allow the charge that already been stored in the capacitor that is feeding the logic part to go back to the battery or go back to feeding the pack, the main transistor transformer driver, which is the MOSFET at the output. And then this capacitor C5 is connected at the inputs after the diodes. That's at the output after the diodes, after the power diode. And it was 1000 UF before, but I changed it to 4700 UF for more stability. So this capacitor fit the entire logic circuit irrespective of the other capacitors that are individually connected close to other logical parts, but this one fit the entire logic part. So from this capacitor we now have this voltage regulator, 5 volt regulator, which fits the signal generator here. A 5 timer is used for the signal generator. So it fits the signal generator, and then it has some other capacitors too to still maintain stability in voltage whenever the system experiences input voltage drop. So from the signal generator, it moves down to the signal amplifier, which is an OP amp, single input, single output OP amp made from the original components, the transistor. It's not an IC. This is the original component. So from this signal amplifier, it moves to the signal splitter. So now from here, the signal is being split into left and right because we are using a center tap transformer. So we need a left and right output. So the signal is being split into left and right using a bipolar transistor A733 and okay, A733. Now on this A733, there is something that was confusing you people here. I've not made the changes on the circuit here, but I will explain. Now, this is it. On the physical transistor, on the physical A733, this part that you see as emitter is being identified as collector. And this part, as you see, as collector is being identified as emitter. That's on the physical transistor. So when you are connecting this transistor, when you check the data sheet, which will now give you the pin outline. That's the collector, emitter, and the base. What you will do is that on the physical transistor, you will connect this part that goes to the emitter to the collector. That's on the physical transistor. And this part that goes to the collector will go to the emitter. That's what you will do. That's for the signal splitter part. And then after the splitter, it moves down to, I made some change here. This resistor was 1K before, but it's 2.2K. When I cross-check the physical circuit, the one I've designed here is 2.2K. So I've checked it R6, where R6 is that's connecting the LED, that is connecting the LED to ground. Yeah, check it and change it to 2.2K. Then from there, the signal output is further amplified using MOSFET. And then from here goes to the base of the two left and right driver. Then from here, we now have the feedback. This feedback circuit, the purpose of this feedback circuit is that it maintains a stable output voltage and power. In fact, in other words, it is what is maintaining power. It's what is maintaining power in the system. So whenever normally you notice that for those of you that have been designing an inverter without feedback, you notice that when you load it, the voltage drop. But with the feedback now, when you load it, if you set the voltage as 220, at 220 or at 233 or 240, when once you load it, the voltage will remain the same, except the load you put on it is above the battery capacity. That's when the voltage will drop. So that's the purpose of the feedback. So I think that is it for now. And then we are going to work on the transformer so that we can move on to testing the feedback, because this feedback there might still be some adjustment to make based on after tests. So that's it for now. So I'm going to still make a video to explain some other further things. So please, thank you for your time.